Okay class, we are looking at selection of multiple choice questions for our rational functions, which is of that form. Rational functions, y equals a numerator divided denominator, and we're going to have power functions for the numerator and denominator, and also for reciprocal functions, where it's the reciprocal of a function of x, which is going to be a polynomial of a sort. Okay, let's get into it. These are multiple choice questions. So question 1, the graph with equation y equals 1 over 2x squared minus x minus 6 has asymptotes given by. Alright, so here's a reciprocal function. We're looking for the asymptotes of a reciprocal function. Now, we have to identify that generally a reciprocal function has two types of asymptotes, a vertical asymptote. Okay, now your vertical asymptotes we focus on when the denominator, our f of x, when that is equal to 0. That's when it's undefined. Okay, so if we look at our quadratic we have in the denominator, 2x squared minus x minus 6, and equate it to 0, and we solve for x, then we're finding the vertical lines of the asymptotes. So one way you can do this quickly on the CAS is to factorize this quadratic. So we use the factor function of the CAS, and that will give you brackets there, double brackets. Otherwise, when we are factorizing, we use a method where we go 2 multiplied by the negative 6 to give a negative 12, and then we find factors of negative 12 that are going to add to give us the negative 1. In this case, 3 and negative 4. Okay, so we express the quadratic in this form, and then we factorize. And we find we've got another common factor of x minus 2 in each pair of terms. Take out that common factor. There we go, equate it to 0, and then we can use null factor theorem and solve for x. So here are our two vertical asymptotes. Okay, and then the second type of asymptote that a reciprocal function can have, being there's two types, is a horizontal asymptote, or sometimes a slant asymptote. Okay, in this case we've got a horizontal asymptote, alright, and this is when as x approaches a very large number, as x goes to infinity, then the reciprocal function here, as the denominator approaches a large number, x, the function approaches 0. So we get a horizontal asymptote at y equals 0. So that gives us, there's the third asymptote, and that is option D for our three asymptotes. Okay? Let's have a look at the next question. So the features of the graph of the function with rule. Okay, so now we've got a rational function of a quadratic over a quadratic. Alright, so we have to identify the features, and the kind of features we're looking for are asymptotes at a certain point and a point of discontinuity. So another word we used in class for a point of discontinuity is called a hole. What are the holes in the graph? Okay, so the first thing we're going to do is factorize our rational functions. Let's factorize the numerator and the denominator, and let's look for any common factors that we have. So then there we go, there's our double brackets. And we can see, look, there's a common factor of x minus 3. Okay, so when we divide our common factors, we can simplify our rational function. But you have to be careful, because the whole idea of dividing this common factors gives us an equivalent form, but the point of discontinuity is going to lie at that x equals 3 value. So as soon as you divide out a common factor, that x value for the factor, that's the point of discontinuity. That's where the hole in the graph is going to lie. Okay, so we found that point, that feature. Now let's look at what we have left. There's our rational function in simplest form, and we can identify an asymptote when that denominator x plus 2 goes to 0. So that is when x is equal to negative 2. Okay, so put those two together, x equals negative 2 asymptote, and a whole at x equals 3 gives you option D as the correct result. Okay, next question. So question 1, the graph of the function with the rule f of x equals 2x minus 1 on x squared. Okay, it has asymptotes or local minimums or maximums at a point. Right, so to find asymptotes of this function, that's the first thing we could look for. Okay, we can identify a vertical asymptote when the function is undefined. That is when the denominator here goes to 0, and that occurs when x equals 0. Alright, so we've got one asymptote we've found so far, but you've got to be careful because there could be another asymptote called a horizontal asymptote or a slant asymptote. Now, this occurs when we take the limit as x approaches a very, very large number. Okay, so if as x goes to infinity, what happens in our function? Well, if you have a look at the denominator here, it's a squared term, and a squared term is going to approach infinity a lot faster than a normal x term. Okay, so this 1 on x squared term will vanish and go to 0 really, really quick compared to the 2 times x term. So we have an asymptote tending towards here, y equals 2x. That's the line of the asymptote, of our slant asymptote. Alright, so we've identified 2 asymptotes there. Now, let's look for stationary points. There's our minimums and our maximums. So, to find a stationary points, let's first rearrange our function and write it as a negative power. And then let's find the gradient function, f dash. So after differentiating, we get this, 2 plus 2 times x to the power of negative 3. Now the stationary point occurs when this gradient function is equal to 0, and that will give us our stationary point. And from there we're going to solve for x. So this is a 2 over x to the power of 3. Now that is equal to a negative 2 after subtracting that positive 2 to the right hand side. And then when I do the reciprocal of both sides and divide and multiply by that 2, I will get x cubed is equal to negative 1. And taking the cube root of negative 1, well, that gives me a negative 1. It's not the same as doing the square root, because the square root of a negative number is imaginary, but the cube root, well, that's a real number. Alright? Okay. So we have our stationary point at x equals negative 1. Well, that's good. We got that. Now, how do we know if it's going to be a minimum or maximum? Well, one thing you will learn how to do is something called a sign test. And a sign test can help us work out if a stationary point is a minimum or maximum. But we're not going to use that method in this video at the moment, because that's for a later stage when we learn more about the sign test. But for now, being a multiple choice and exam 2 type question, the CAS calculator is allowed. So one little thing you could do is do a little sketch, quick sketch of a 2x minus 1 on x squared function in your CAS, and you'll get something a little bit like this. Okay, and there you can see is the asymptote, one asymptote there. Then you've got another asymptote being a slant asymptote here, y equals 2x. Okay, and then at this point x equals negative 1, so that's to the left of the origin. Here, well, we're talking about this stationary point, and as you can see, that is a maximum, a local maximum stationary point. Okay, so hence it must be option E that is correct. Alright, so how are we going so far? Let's go to the next question. Now the graph of this reciprocal function with a quadratic in the denominator. Okay, so we're told that it has an asymptote at x equals -5 and x equals 3, and a third asymptote, horizontal asymptote, y equals 0. And then we've got one stationary point, and this stationary point has a y coordinate. All right. Now, this is a bit like working backwards. We're given the shape of the function, and our job is to work out what the a, b, and c parameters are in the reciprocal function. Okay, so the first thing we're going to draw on is the information about the asymptotes. Now, the asymptotes occur when the denominator is equal 0, and we can find equations of the asymptotes easily by normally starting with this quadratic. We factorize the quadratic and then use the equator to 0, use the null factor theorem to solve for x. Okay, now, so that means our one-on function of x could be written, this function of x could be written as a pair of double brackets. Okay, so where the parts in the equation with the double brackets is always opposite the sign of the number for the equation of the asymptote. Now, because we have a factor of a here multiplying the x squared, we're going to include that factor a there. So when I go ahead and expand, multiply a through as well, I get this. This is now the same form as the form given in the question. Okay? And now we can, make some connections. We can see that parameter b, well, b is the same as 2 times the a, and parameter c, well, c is the same as a -15 times a. All right? So we'll draw on that information a little later. All right. Now we're going to draw on the information of the stationary point, because we're going to use that information to help work out what the a parameter is going to be. So stationary points occur when the derivative of the function is equal to 0. Now, if you remember from our class notes, if we differentiate our reciprocal function, then and we're finding the stationary points by equating the derivative of this reciprocal function to 0, it's the same as just differentiating our denominator to getting f dash and equating that to 0. Okay, they are equivalent expressions of finding our stationary points. So I'm going to use this form of the function f of x, okay, because it's only got the one unknown in it, unknown a. Here we go. There's the gradient function. 2 times ax plus 2a equals 0. And by solving for x straight away, I get x equals -1, because the factor of a there, well, that actually cancels out through division. So I know where the stationary point, the x value for the stationary point is straight away, x equals -1. Now that's very useful, because now I know the whole coordinate where the stationary point occurs at. I have it occurring at x equals -1, but from the information in the question, I have the y coordinate of the stationary point is -1/8. So that's the whole x and y coordinate of our stationary point. So let's use that, and let's substitute that into our function of x, into our reciprocal function, that is. So substitute the y coordinate of -1/8, and I substitute in -1 into the quadratic at the bottom, into the x squared, and then the x. And now I'm going to simplify the denominator there to give us a -16a. And by taking the reciprocal of the left-hand side and the right-hand side, I can form this equation. -16a is equal to -8. So that means a must be a half. Okay, we've got our a number. And so because I've worked out a, I can quickly do a check with the multiple choice options, and I'm crossing off the wrong answers there, where A is not equal to a half. And that just gives me two options now, A and C. So if I'm a gambling man, I can flip a coin and, 50% chance is pretty good. But let's draw on the last bit of information to work it out exactly. Now, if I come back to the equation, the only things that are unknown now are B and C. But hang on. Parameter B is the same as 2 times A, and the parameter C, well, that's the same as the negative 15 times A. So let's use that. There we go. I can substitute a value for A in, and I get B is equal to 1, and C is equal to negative 15 on 2. So, voila, there it is. Option E is the correct one. All right, that was a little tricky one, but you have to really test your understanding of things like asymptotes and how to find stationary points. Fantastic. Let's move on. All right, so the number of straight line asymptotes of this graph now are a rational function. Now, this is not a pretty graph to work with. I've got a cubic over a quadratic, not good. So let's rearrange this through division, okay? So that's the first thing we're going to do. Let's do long division of polynomials. There it is. The first line, x squared, divides into the 2x cubed, exactly 2x times, and then I multiply that back into the divisor. Then I subtract to get a partial remainder. And I've got to be careful here. I've got a subtracting a negative 4x from a 0x term, so I have to make sure I take that into account. All right, there's the remainder I got. And then a little bit more. I now do the division x squared into a 3x squared, goes exactly 3 times, and then I take the 3 and I multiply it back into each term in the divisor and record it down the bottom. Do the subtraction to get the remainder, and there it is. 7x plus 5 is the smallest remainder I have there. So then I'm going to represent my rational function now in terms of the quotient plus the remainder divided by the divisor. Okay, that's important to know that structure. For any, here we've got a polynomial, think of it as a polynomial over a divisor. Well, that's the same as the quotient plus the remainder over the divisor. Okay, so there it is. I have a new form. Now, I can already identify a few things from here. Well, I know that I'm going to have some vertical line asymptotes when the denominator here goes to 0. And I may have a slant asymptote depending on this term as x approaches infinity. Okay, so first thing we got to do to just to confirm that is we're going to factorize the denominator. There it is, double brackets, x minus 2 times x plus 1 are the factors of that denominator. And from there, I can work out what those equations of the asymptotes are. All right, so that's 2 of the asymptotes. And then we're going to have a third one from the slant asymptote. So its option is D. At this stage, we can answer it already. But let's just go through and work out what they are as a practice as well. Okay, so the slant asymptote there, as x goes to infinity, we're going to have the graph tending towards the line 2x plus 3. And there's your slant asymptote. And then your vertical asymptotes here when the denominator goes to 0, so that's at x equals 2 and x equals negative 1. Fantastic. All right, option D. Let's do the next question. Okay, so now we've got a graph of a rational function, and we're going to have to figure out what's the equation. Now, first thing to recognize, hey, we've got this, like this parabola, which is acting like a bit of an envelope. All right, it is like a slant asymptote. Okay, So the graph runs along x squared. So we have, in fact, an x squared term that is going to be in our equation. And as we've also have here another asymptote, a vertical asymptote, because the graph comes up and then runs asymptotically vertically upwards like this at x equals 0. So what kind of function gives you a vertical asymptote at x equals 0? Okay. And then what we should recognize here and is on this side of the graph, when x is positive, we have the graph of y values is also positive, but same on this side, when x is negative, y is positive. So what kind of function creates a positive y value when x is negative? It might be a squaring, or it might be to the power of 4, it might be to the power of 6. Alright, so let's put a few things together. To get our vertical asymptote at x equals 0, we need a reciprocal function of x. Okay? So when x is 0 here, we've got an undefined value, and that is our vertical asymptote. Now, for the y values to be positive, okay, I must have one on x squared graph, because here when x is negative, negative times negative, well, that goes to positive, so I get my positive function there. So I've definitely got this term in my equation. Okay. Now from the slant asymptote, all right, the slant asymptote adds as another term in the equation. So I've got a y equals x squared as well. All right. Now this here, 1 on x squared, well, that's a truncus type shape, produces a graph that looks a little bit like this. Just do it quickly. Yep. Okay. And this kind of graph, the summation of ordinates of this graph with our parabola here, well, that definitely seems to fit to make our function of x that is given in the graph. Okay. So this here is, because it's summation, any numerator must be a positive one. Okay? So if I put the information together, I'm going to have the slant asymptote, here's the x squared term, plus there's my it could be any number, it could be positive 1, positive 2, positive 3, but it has to be positive, okay, because it's got a vertically positive y values there. All right? And if I rearrange it with a common denominator of x squared, then I get x to the power 4 plus a, for a must be a positive value. Okay? And there's our correct option, that's option D there. So that's an interesting question. It really tests your understanding of the features of rational functions there. Okay, next question. Now this one's similar. This time we've given the given the equation, and we're going to have to work out the graphs. Which one's the correct graph for that? Okay, so this is x to the k plus a on x type thing. Now k is odd integers. So odd integers like, your 3 and your 5 and your 7. So we're going to have this term here could be an x to the power 3, x to the power 5, or x to the power 7. Okay? Now, as soon as we divide by x, having a denominator of x, well, this is going to produce, when we separate it, I get this type of function when I rearrange it through division. Okay? Now, this x to the k minus 1, now, what is that going to be like? Well, if k is a 3 and a 5 and a 7, then k minus 1 must be a 2, 4, 6. Even functions. Okay, and what does that look like? It's going to produce this kind of positive parabola type shape. Okay? So even when x is negative, y is going to stay positive. All right? Now, the next thing we have to think about is this term here, the a on x term. Now, that is your rectangular hyperbola. But if we look at the information about what is a has to be negative here. So we have to reflect. We have to reflect our rectangular hyperbola. Okay? So the a on x graph, when a is negative, that's going to look a little bit like that. Okay? When x is negative, y goes positive, and when x is positive, y goes negative. That's the reflected rectangular hyperbola. So if we put these two together, okay, first off we can recognize that this quadrant of the graph, well, y is positive, and in this quadrant of the graph, y is also positive. So the summation, the addition of ordinates of these two graphs, where y is positive plus another y is positive, the addition of ordinates, the summation graph, must be also positive in that quadrant. So it can't be this one, can't be that one, because this one has, it does have y as positive, but it's also got this negative section there. And it can't be this one either, because there's that negative section, even though they're all positive and all positive here. All right, so we've eliminated 3, and look, 2 options, 50-50, pretty good. Let's think about the other side of the graph when x is positive. In these quadrants, there and there. All right, we can see, hang on, in this quadrant, the first quadrant, y is positive, but in this quadrant, y is negative. So, and this is a pretty strong negative here. Look at that. That's asymptotic. So for very small x's, that's this part of the rectangular hyperbola is really going to drag down the summation graph. So, and we can see that same feature here, really drag down. Okay? And that's definitely the correct one. E couldn't be right because, look, there's no negative part at all. I think it's all positive, which isn't correct. Must be a little bit negative. All right, so how'd we go with that? So the best way to approach that problem is to split it up and think about one section of the graph at a time, understanding the features of the two graphs that you add together through addition of ordinates to get the summation graph. Okay? Lucky last question. Coming to the end. This has been a great task, this one. I hope you've learned a lot. Now, question 3. The graph of y equals a function of x is shown below. So that looks like a bit of a reflected parabola, negative x squared type graph. Now, it says all of the axes below have the same scale as the axes in the diagram above. Well, that's good. Now, the graph of the reciprocal function, y equals 1 on f of x. So, that is best approximated by which graph? Let's think about the features of reciprocal functions. Okay, reciprocal functions. So, first thing to identify, hey, look at that. That's the graph crosses the x-axis. The y value is 0. So, whenever I get an x-axis intercept, the reciprocal function produces an asymptote. That's the one important fact we need to know. So we're expecting an asymptote at x equals minus 1 there, or close to it. So, where is that? It's definitely not this one. It's definitely not this one. It could be C, it could be D, or it could be E. All right, what else do we have? Well, let's have a look at our maximum stationary point, a maximum turning point there. Well, that is, if I read it from the graph, that's approximately 3 on 2, 1.5. Okay? Now, if I do the reciprocal of that value, I get 2/3, which is down here. So I'm going to end up with a local minimum. If I've got a maximum in my function of x, then in the reciprocal function, that turns into a minimum. So there's the minimum, and I have the opposite kind of direction. So as f of x decreases, then 1 on f of x, the reciprocal is going to increase up to that asymptote. So I've roughly drawn this part of the graph. Now let's try and match it. Definitely not that, definitely not that. Doesn't look like that at all. Or maybe C, maybe E. Well, they're pretty close. I think, in fact, have a look, being a parabola, look at this region here. Well, f of x, that is decreasing there, and the reciprocal function must then increase at that little section. And that corresponds with here, very carefully. Not C, because C keeps decreasing and decreasing and decreasing for the graph, and that's not right. That's not the behavior we are showing here. Alright, so we've narrowed it down nicely. It must be option E is the correct graph. Okay, fantastic. Now, let's just do a quick recap of those properties of, for a function of x, what is the reciprocal function property. So, for a function of x, as the y-coordinate for f of x is increasing, then the reciprocal, the y-coordinate, is decreasing. Okay, and vice versa. If y is decreasing in the function of x, then y is increasing in the reciprocal function. Now, any x-intercepts you find in the function of x, they are vertical asymptotes in the reciprocal function. And a maximum turning point becomes a minimum turning point in the reciprocal function. And vice versa, the minimum turning point becomes a maximum turning point in the reciprocal. Okay, they're crucial facts that you need to know when you're examining reciprocal function graphs. Other little things that are the same between a function of x and a reciprocal function, well, whenever the function of x is positive, the reciprocal function will also be positive. And when the function is negative, the reciprocal function will also be negative. So it's also good to keep that in mind. Fantastic. Well, we've come to the end of our quiz. Everyone's done very well. Keep practicing.